Good day, Math 30-1s. Today we talk a little bit about something new, a continuation on powers, on exponents. And this time we start to graph and look at exponential functions. What does it look like? Now the big difference between what we've maybe talked about previously is considering y equals x squared versus y equals 2 to the power of x. How do those differ? Which one grows faster? How do they compare? And this is what we're going to examine today, is when your letter, when your variable is in the power position. And this is called an exponential function. What could change is there could be a new number there. It could be a 3, 4, 5, a 1.2, a 0.75. We're not going to deal with negative numbers there, but we are going to consider bases. Positive, fractions, whole numbers, exponential functions. The point of today is to look at some characteristics. So what does it look like? What if maybe we start to talk a little bit about maybe a vertical stretch? What if we talk about a base value that's not 2 or a 3 or 4, a big number? And we're going to maybe involve some problems as some applications. Now, to really understand exponential functions, it is important to know there are some rules that you've examined in junior high and maybe in grade 10. So first, as an introduction, negative exponents. They mean something. If I were to ask you what is 2 to the power of negative 3 without a calculator, what does it mean? What would you say? Well, if you kind of examine what happens if you plug some values into the power position, like what if I were to plug in 3? So I say, what is 2 to the power of 3? Well, 8 comes out. 2 times 2 times 2. What if I plug in a 2? Well, 2 squared is 4. Let's keep going. 2 to the 1, 2 to the 0, and all of a sudden, it doesn't really make as much sense to say 2 times 2 times 2, 2 times 2, 2. And what does it mean if I say 2 to the power of 0? It sort of defies logic a little bit, but there is a pattern that allows us to determine values. 2 to the 1 is a 2. And if you look at this pattern of divide by 2, divide by 2, divide by 2, I'm running into my notes here. Divide by 2, a half divided by 2 is a 1/4, and a 2 to the negative 3, divide by 2 should be a 1/8. Some of you might remember that if you're dealing with a negative power, it actually is more of a position. You flip it as a reciprocal and deal with a positive power. So we're dealing with negative powers are actually more of a position, a reciprocal. If we're dealing with 0 powers, we saw this over here, 2 to the 0 has a value of 1. 5 to the 0, 10 to the 0, anything to the power of 0 has a value of 1. And this does become important as we start to examine a sketch of what an exponential function is, and if we're dealing with an x value of 0, where are we on the graph? In fact, we'll be at a y value of 1. So we are going to need to be plugging in zeros. We are going to be needing to plug in -1 and -2 and -3. So these negative values are essential for understanding the visual, the graphical side of this. But there were some other rules talking about 2 cubed times 2 to the 4. How do we write this as a single base of 2? 2 cubed to the power of 4. What do these mean? Well, 2 to the power of 3 is repeated multiplication. 2 times 2 times 2. 2 to the power of 4 is 2 times 2 times 2 times 2. And there's a product in between that. So really, this is 2 7 times. And we can write that as 2 to the power of 7. Now, in fact, what's happening is we are dealing with an addition of the powers because we're dealing with a lot of repeated multiplication, which is similar to a 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 3. And you could use this previous logic to say we're adding 3 4 times, or 3 times 4. This is in fact a product when you're dealing with a power on a power. So 2 to the power of 3 times 4 is 12 is your answer. So base with a base, we're adding. Power on a power, product. A radical with maybe an index of 2 as a square root is actually a fractional power. So if you're dealing with an index or a root of 2, the only thing that changes is your power actually has a denominator of 2. So the index is the denominator of your power. So if I were to say 2 to the power of 7 as a cube root, we could write this as 2 to the power of 7/3. And lastly, we're dealing with some logic that's going to be essential for this next unit coming up. And I could write the number 8 as a base of 2. 8 is 2 cubed. And if nothing else changes, we could actually see we're dealing with a power on a power, a product. And what is 3 times a binomial? Well, the 3 would have to distribute into both of those, and you'd end up with a 9x minus a 12. There is a single base, single base, single base, single base, all of 2. So there are some previous rules that are going to be essential to understanding what we're doing. And as we move into the visual side of things, it is important to remember what exponential data is. Exponential is like multiplication. We're dealing with multiplying the same ratio each time. This was introduced in grade 11. Now, arithmetic growth or linear growth is quite slow. We're adding 2 every time. Plus 2, plus 2, plus 2, plus 2. This is arithmetic growth. You're adding the same number. It's very slow. We could get this by saying the first number is 2, the second number is 4, the third number is 6, the fourth number is 8. Really, you're just multiplying the location, maybe n or x, by 2. So the fifth location would be 2 times 5, 10. Okay, very slow. This grows as a linear path. Exponential growth is saying not plus 2, plus 2, plus 2, but times 2, times 2, times 2. And I'm picking on the number 2 right now, but I could say times 3, times 3, times 3, times 3, and it's still exponential. But how do we get this? Well, we're actually saying to get the fourth location, you'd have to say 2 to the power of 4, or 2 to the power of 3, or 2 to the power of 2. I'll just call it an x for right now, but if I wanted the fifth location, which would be a 32, I would have to say 2 to the power of 5. But it's the power that becomes the 5 or the 6 or the 7. It's the power that changes. And this is going to start to grow much more quickly, and it will curve. In fact, more sharply than a quadratic x squared. So there is a standard form of what an exponential function looks like, and it's kind of like this. We can have some base, like a 2 or a 3 or a 4, or whatever number we want, to the power of x. We can also have, though, some number in front, and this might be some vertical stretch to make this stretch up a little bit, and it can mean a little bit more as we deal with applications. As a visual, A represents your y-intercept. If your x value is a 0, b to the 0 is a 1, and it really has no effect on anything other than the a value becomes what's left over when x is 0. So it could be a y-intercept, but it could also be a starting value if we're talking about applications. So for applications like mitosis, cell division, finance question, maybe we're talking about radioactive decay. All of this refers to applications. B value represents some rate of change. So it's the ratio. It's the value that matters most. Okay? It is how we're multiplying every time. And sometimes it's times 2, times 3, times 4, times 1.3, times 0.75. Whatever this base is how it changes from one term to the next. So let's try examining some graphing, and we'll kind of speed through a couple of these. But we'll first look at, and I'm picking on some nice base function, 2 to the power of x. A really nice function to start with. So we'll do this with a table of values to start, and let's say input, output. I'll pick a few inputs like -3, -2, -1, and 0, and a 1, 2, 3, maybe even a 4, and we'll see where this lies. As we plug in -3 into 2 to the x, we're asking what is 2 to the -3? A negative power. This is a 1 divided by 2 to the +3, or 1 over 8. As a decimal, it's about 0.12, and we'll use that to approximate things, but it's 1 over 8. Then we've got a 2 to the power of -2, which is 1/4. 2 to the -1 is 1/2. And as we continue with this pattern of times 2 times 2 times 2 times 2 times 2, we're building this exponential pattern. So what we have is a -3 getting plugged in, and a 0.125 comes out. Plug in a -2 and a 1/4. Plug in a -1 and a half, a 1, a 2, a 4, an 8, and then a 16, 10, 11, 12, 13, 14, 15, 16. And this curved shape is your base function for y equals 2 to the power of x. Okay. It's interesting to note what happens as we move to the left. What if we plug in a -4? Would we be at 0? What if we plugged in -10? Would we be at 0? What if we plugged in -100? Let's use that as our last example. What if I say, where are we at for -100? Well, we have 1 divided by 2 to the +100. Is that 0? 1 divided by a giant number, it's not actually going to be 0. What if I were to say 10,000? Will we be at 0? Will we ever get to 0? What we start to see is, for the very first time, a horizontal asymptote where it levels off infinitely close to the x-axis but never actually gets there. So we are dealing with a horizontal asymptote that is the x-axis. Eventually we'll talk about shifts up and down, which will change that asymptote, but for now we are dealing with the x-axis as a horizontal asymptote. For our next one, we're going to deal with a new change, a vertical stretch by a factor of 3. And all we're going to do for this one is take our previous chart, which is really the same graph but vertically stretching up. At -3, we were at a 0.125, but we're going to stretch it to be 3 over 8. It's a little less than a half. 3/4. 3 times a half is 1.5. 3 times 1. 3 times 2, 6. 3 times 4, 12. And I think that's as far as we can get. 24 would be next. And what you can kind of see is this idea that it is growing a little bit faster than this one. It is a vertical stretch by 3. Let's say stretch. Now this is a base value like 2. We could have started with a 3 or a 4 or something bigger, but we can also deal, though, not with sort of growth, but with a bit of a decay or a reducing exponential function. A 1/2. We'll do this once with a table of values, and maybe we'll even skip the next one if we're understanding this. What if we plug in a -3, -2, -1, 0, 1, 2, 3, 4, same kind of values that I'm choosing around x? What is a 1/2 to the power of -3? Again, what happens is it flips to a 2 to the +3 power, so 2 cubed is an 8. You can use your calculator to double check that if you wanted, but we're dealing with, again, this negative power, the 2 flipping up to the top. A half to the -2 is a 2 to the +2, or a 4. In fact, what starts to happen is we're dividing by 2 each time. That's what the 1/2 base means. That's your ratio. Times by a half, times by a half, times by a half, times by a half. In fact, we're dividing by 2 each time. So as you plug in these values, like at -3, we're up to an 8. We're then at 4 and 2 and 1 and a half and a quarter and an eighth and a 16th and so on. We're really dealing with this graph as a horizontal reflection in a way. This is a decay, but in a way it's a horizontal reflection. And we could do the same thing with a vertical stretch by a factor of 3 to see what that looks like, but in fact it would kind of work. What are some key things to note about exponential functions? Well, maybe we could say the domain goes forever left, forever right. There's no real restrictions on it. As a range, it's everything above 0, doesn't actually get there. And there is a nice y equals 1 as a y-intercept, unless we start to talk about an a value, or unless there's eventual stretch or shift or flip. Now, if we're trying to go backwards, it is an important thing to understand that when you look at a graph, there's a nice way to pull information out of here. What we're looking for is two things. Remember, our equation is a times b to the power of x. We're looking for a ratio. How does it change? And what is maybe a y-intercept? So I can look at this graph here, which has a bit of a unique scale, horizontally going from 0 to a half to a 1 to a 2. So we're skipping 1 each time. So what if we were to write down all the y values as we progress? The y values were a third, and then they were a 1, and then they were a 3, and then they were a 9. How do the y values change as we move up by x each time? Looks like we're multiplying by 3. Your ratio, your b value, is 3. What is your y-intercept? 1. So we can simply say it's 1 times 3 to the power of x. And in fact, that 1 it really isn't necessary. So this is the graph of 3 to the power of x. Let's try one more, asking how do the y values change? Where it looks like we're going from a 1, 2, 3, 4. Looks like we're going from a 4 to a 2 to a 1 to a 1/2, and so on. So it looks like we're dividing by 2 or multiplying by a half. We're multiplying by a half every time. As an a value, it looks like we're starting at a 2, a y-intercept, and there is your nice equation. So look for a pattern in the ordered pairs. As x goes up by 1, how does y change? And the y-intercept is your a value. And the last big conversation today is to talk about applications of exponential functions. So really the question is, can we model something in the real world? We know when we talk about mitosis, cell division of bacteria doubling every few days or hours, it's this doubling which is exponential. In finance, we talk about percentage growth, and that's a little bit of a unique conversation. We could talk about a times b to the power of x, but something unique can happen if we start to talk about things like how long does it take for some doubling to happen. That's important. So it's important to know that a b value of 1 has no effect. A b value of 1 is really unchanged. If you're multiplying by something bigger than 1, your values get bigger. If you're multiplying by a number like a half or a quarter or a 0.95, your numbers are going to get smaller. So if I were to pick on a base value that was less than 1, I know that my values are decreasing. In fact, it's 5% away from 1, so we're decreasing by 5%. If I say 1 point something, we're increasing by 5%. 1.05 increasing by 5%. So these two numbers, while they look very, very different, are both talking about 5%. One is increasing, one is decreasing. How far we're away from 1 is a percentage increase. If the base was 2, we're doubling. If the base was 5, we're increasing by a factor of 5. But percentage growth is really a shift away from 1. And there is this new value at the bottom in the denominator position here. P represents the time for some growth to happen. So I'm going to change these questions a little bit below to be a little bit more interesting. A colony of ants starts at 50 and increases by 15%, let's say every 2 days. So we have this equation where there's an A starting amount, some base increases by 15%, increases by 15% every 2 days. Now my t value, my input, is a time in days. And now if I wanted to know how many ants will there be after 10 days, I plug 10 into the t, and out comes the number of ants. Simple as that. What about an investment depreciates by 20% every 3 years? We could say that a $40,000 starting amount loses 20% or keeps 80%. We're 20% away from 1. That's what we're losing. So we're keeping 80% every 3 years. And now input is going to be in years. So if I want to plug in 5 years, 5 goes into the t. This is a way to model exponential equations, which we're going to build on in the next day. But this is a nice starting point. The last one to really actually try to work on is still an application, but this time about radioactivity. And it's a really interesting conversation to talk about how radioactive material breaks down. So in this example, we've got a radioactive sample of radium-225, and we're going to start with 55 grams. We're going to say that its half-life is 15 days. And if you've been in some physics classes, this makes a little bit more sense. But what this really means is that if you've got a sample of 55 grams of this material, if you wait 15 days, that sample of radium is going to break down into some, I don't know what it's going to break down into, maybe beta particles, alpha particles, new materials, neutrinos, but it just sort of